Hello, everyone. So Fred just introduced, more than introduced the Bayesian modeling and this application on M99. So I will continue on a lower metallicity environment, which is the LMC. So first, what are we trying to do? We are trying to quantify the photoelectric heating efficiency in a low metallicity environment, which is the LMC, and to produce a dust properties map. So why, if you look, I won't go into much detail of this plot, but it's typically a cooling function of the ISM. And if you look, you see that the cooling channel change depending on the gas temperature. But the shape of this function will also change depending on the heavy element fraction, so the metallicity and the grain microphysics. So why do we care about this function? Because it will be important for galaxy simulation and also stars formation modeling. So typically, we are trying to constrain this part of the graph. We chose an empirical approach, and more specifically, we chose to focus on the LMC. The LMC, so the Large Magellanic Cloud, is the satellite galaxy to the Milky Way. So it's quite close. It has half solar metallicity. And we are going to focus more on N158, N159, and N160 star forming region, which are south to 30 Doradus. So why the LMC? Because it's close. So we can resolve it in the far infrared at a parsec-scale resolution. And also because it's lossy. So since it's lossy, we can probe different dominant heating mechanism than we can do in the Milky Way. And in our case, it will be the photoelectric heating. So the photoelectric heating comes from the UV light of young stars, which is going to be absorbed by dust grain and going to hit the dust grain. And then the dust grain are going to cool down, emitting in infrared. But a small part of the UV light is going at the contact of the grain to cause the emission of an electron. And this electron is going to collide with the gas around and cinematically hit the gas around. We cannot access directly this heating, but we can access the cooling of the gas. And in the neutral atomic gas, it will be the C+ line at 158 microns. So we can define two proxies to quantify the efficiency. The first one will be the ratio between the C+ and the luminosity of dust. So basically this part. And the second one will be the C+ over the small grain luminosity. Why the small grain? Because since the photoelectric heating happened at the surface of the grain, and the surface is dominated by the small grain, the small grain will control the photoelectric heating. So we need also a C+ map. My work is part of the LMC Plus project, which mapped the 3-star forming region I mentioned earlier. And we are going to use the SOFIA map. So we have a C+ map here and a OIII map here. We are not going to use. But these data are available, and if you're interested, you can look for Fisher et al. 2025. We are going to do acidic fitting, so we also need other data. So basically, data from Spitzer and Herschel that goes from 3.6 microns up to either 250 microns or 500 microns. And we also have ancillary data, so the C+ line, H-alpha map from the Denzel survey, and CO221 map from ALMA. We chose two final resolutions, one at 18 arcseconds and one at 36 arcseconds. I will talk just a bit later on why we have two final resolutions. So the method, Fred mentioned that we are doing spatially resolved LCD fitting. So we need one-to-one correspondence between each pixel for each map. And so we have to homogenize the data by convolution and reprojection. We also estimated and propagated the errors with the Monte Carlo method. And finally, fit the LCD for each pixel using Erlang. Then we created some dust map properties and also finally estimated the efficiency of the photoelectric heating. So just a few words on the parameters we are interested in. We are interested in the monochromatic dust luminosity, which is the L dust. That depends on the microphysics of the grain and also the dust mass and the average radiation field. One main parameter also is the small grain fraction, the QAF. That is the ratio between the dust mass attributed to grain with a radius below 1.5 nanometers and the total dust mass. So a typical LCD would look like this, with the aliphatic and aromatic band here, and the infrared continuum just here. Just note that the red scatter is due to the fact that we are doing hierarchical Bayesian modeling, so it's just the probability distribution of our LCD. So we faced few challenges doing this LCD, because at the beginning we have a C+ map at 15 arcsecond resolution, and we told ourselves, okay, we are going to do spatially resolved modeling at 18 arcsecond resolution, which is the resolution of Spire 250. But we were blocked by the number of dimensions of our posteriori distribution, because as you can see, it depends on little m here, which is the number of pixels, q, the number of parameters, and m, the number of filters. And if you look at the number of dimensions of the full map at 18 arcseconds, it's over 500,000. It's over 500,000, which is huge. And we have a lot of trouble to make it converge. So we decided to decrease the resolution to 36 arcseconds, and we divided the number of dimensions by a factor 4. It was good, but we still wanted to have a high resolution maps. So we decided to do smaller maps on each individual region, star-forming region. And typically, we have for the N159 map, which is the biggest individual map, a number of dimensions around 50,000. So the point is that the convergence and computational time will grow quickly with the map size. How did we make sure that our maps has converged or not? We looked at the ACF. To make it simple, the ACF is just a diagnosis of convergence that we can look, and it looks like this. So on the top, you will have an ACF for the small grain fraction as the function of the lag, which is basically the number of steps of the MCMC. So for the full map at 36 arcseconds, so if it converges, it's supposed to oscillate around 0. And you can see that even for the full map, it started, I think, 1.5 years ago. It hasn't converged yet, and it's still ongoing, but hopefully it will at one point. And for the smaller maps at a higher resolution, it started to converge and to oscillate around 0. Even though it hasn't converged, I will present the result on this map, because if you look at the MCIT, it will only change by a few percent the result. So the first map we looked at was these two maps. So the map of the average starlight luminosity or radiation field and the small grain fraction. What we can see is that where the small grain fraction is low, the average starlight luminosity is high. This is what Fred talked about. And we plotted this graph for two main reasons. The first one is that it was to check the consistency of our results. And the second one was to since the small grain are the dominant in the photoelectric effect, it will impact the efficiency at the end. So the intense radiation field destroys the small grain, and it's a well-known relation. Once we make sure our results are consistent, we could check the efficiency of the photoelectric heating, and the first estimation was to check the C plus ratio, the C plus over the total infrared luminosity as a function of the small grain fraction. So we see that the ratio grows with the small grain fraction, and this is due to the fact that small grain dominates the photoelectric heating. It's a good estimation, but it's only a low limit on the efficiency, and we wanted to get rid of the dependency to estimate the efficiency. And what we did is to plot the ratio between the C plus and the small grain luminosity as the function of the small grain fraction. So this is what we've done, and you can see that we flattened the correlation, but we have a huge dispersion. But if you compare it to the typical error bar, the typical error bar is quite small compared to the dispersion. So we told ourselves, okay, this is likely due to the variety of physical conditions in the field of view. And we wanted to make sure it was the case, so we did the same plot, but on one region. And this is what we had. So we do have a flat relation and a smaller dispersion, but you can maybe see it, but we made some fit to make sure it wasn't an optical illusion. But above, let's say 5% of QAF, you see a slope that appears. And this is likely due to the fact that we only take into account the C plus luminosity. And for a denser region, we should take also into account some other tracers, such as O1. I mentioned at the beginning of my talk that the C plus trace the cooling of the gas linked to the photoelectric effect, but only in the neutral and atomic region. But in fact, we also detect C plus from ionized and molecular medium. So we wanted to get rid of this contamination in our estimation. And what we did is that we used the ancillary data to modelize the C plus luminosity from the ionized phase, which is proportional to the H alpha luminosity, and also the C plus luminosity from the molecular phase, which is proportional to the Coulomb density of H2, also proportional to the CO221 map. So we also suppose that in the atomic phase, all the C plus we see is linked to the photoelectric effect. So we can define the epsilon P, so as an efficiency for the photoelectric heating, and plot the same plot as before. And what we can see, so the red contours are exactly the plot I showed you before on the full map, and the blue histogram is the new efficiency corrected from the contamination of other phase. So you see that we still have the same shape from the histogram, the same dispersion, and the same order of magnitude, but it shifted from a few %. So just to conclude, we can say that C2 over the small grain luminosity is indeed a good estimator. The phase decomposition provides some correction, but it's only by a few %. And we are aware of the limitation of our study, especially in the densest region. And also, I want to emphasize the fact that even if the convergence is slower and takes way much more time. On big maps, it's still doable, and especially stay tuned for the new public version, the first public version of RB with the stellar population and some parallelization included. Thank you.
Thank you very much, Leo, for the talk. Are there any questions in the room? Okay, I have one, just because of this last slide. Do you expect the parallelization to help a lot, considering the number of parameters you have?
So I've run some tests, and the thing is that the parallelization is not on the spatial side of the grid. So it will only improve. So now it's improved by a factor 4, but only on small map, which are dominated by the number of three parameters. And likely on the biggest map, it won't improve by a factor of 3 or 4.
Okay.
Will be less.
Okay, thank you.
I have a naive question. When you define the small grain by having a dimension smaller than 1.5 nanometer. So you are here in the molecular region. So for you, this small grain or PAHs, is it a good word to name them, or do you think to other specific molecules?
So these small grain are in fact defined in the Themis model we are using. So there are no PAH in the Themis model. It's only small silicate and small anamorphous carbon.